Hi, this is Ida Quita, and welcome to Episode 7 of the walkthrough of the HackerRank C language track. We'll be going through the Arrays Introduction Challenge, using our knowledge of pointers to dig out some good stuff on this exciting topic. I'll point out C++ tips and potential pitfalls, but you really need to do this yourself to get value out of the challenge. Be sure and get a HackerRank account. So you can. Please note that the website and all content from HackerRank is their copyrighted material, which I'm using for educational, fair use purposes. Arrays are a way we can use an integer as an index to get into a series of elements. You can see here that it has a new form of declaration, and the way we use it is to reference it inside square brackets. That's the index. There are 4 things that you should know about arrays. You declare them by appending a size value in square brackets to the variable name. You can see 2 examples here. One declares a 4-element array without initializing it, and the other declares a 3-element array and initializes it. Note that when you supply an initializer, that the size is inferred from the size of the initializer. They are 0-based. That means the first element is element 0. So when I output array entry 1, I'm actually writing the second entry of the array. Third, when passed to a function, you can pass it as an array with just empty size. You can pass it as a pointer to an integer, or you can pass it to as an array with a size. This size doesn't do anything, and in fact, the most common way you'll see it is this form, because the array, when it's declared, is really just a pointer to the first element of the array. When you think about arrays as simply pointers, and then with some interesting semantic sugar to make getting to the elements easier, this will make a lot of sense. Let's reiterate that we can interchangeably use pointers and arrays. A of n, the nth element of A, is the same as adding n to A, meaning we're going to take the address of whatever this object is, and we're going to step in memory n object sizes. N times the size of an int, n times the size of a double, n times whatever this is an array of, and then we can get the value operator to get the value that's at that location. And the same thing, the address of the kth element is identical to adding a plus k, the pointer value a plus k. We'll use this in the challenge, and hopefully it'll make some more sense when we're done. So what is the challenge? We're going to be given an array of n integers, and we want to print them out in reverse order. We're given some constraints. These will come in handy as we haven't learned how to make variable-sized arrays yet. The input and output format is that the first line contains a number of integers, and those integers are on the next line. Note that they promise that numbers are going to be, the size of the array is going to be less than or equal to 1,000. That's useful. Let's go ahead and put our documentation in. It's always important to document what you're doing so you know what you're doing. Because if you don't know what you're doing, then anything you do would be correct. And of course, the test isn't going to agree with you. So we're going to say where 1 is less than or equal to n is less than or equal to 1,000. So the input contains n, where n is the number of integers. The next line contains n integers separated by spaces. The constraints are as follows. I think I've got that translated correctly. The output format, print the integers of the array in reverse order. All right, the first thing we need to do before we read data is have some place to put that data. So let's declare our array. So what size do we want to make it? Well, we know that n can't be bigger than 1,000. That's good. That made this problem simpler. And we can read in how many we're actually going to get to another variable that carries the count. What we need to do here is to make sure the count is in range. If the count is out of range, if it is less than 1, or, that's illogical, or if it is greater than our limit, then we can't do anything. And we should tell the operating system that bad things are afoot. The parentheses are there to clarify. The operator precedence would have done these comparisons before the OR, but it's always clearer to group each comparison and then do the logical operations on them. When in doubt, add parentheses. Well, here, this is an error. Let's report it to CError. And let's make sure that that works. We'll give it a custom input and test it. We're going to give it 10,000 and let's see what it does. It says compilation was successful, but there was no output, and the error was that the count was greater than the limit of 1,000. Well, having the same number in 2 places, well actually now 3 places, is really quite ugly. And so in real programs, we tend to define constants. There's a modifier for each type that you can say, hey, this is a variable that I don't want to vary. So I'm going to say limit or max count. And I'm going to initialize it to 1,000. Since the compiler knows what this value is and it cannot change, I can use it like I would a number. And I'll put it everywhere that I need it. It is common in some practices to put constant numerical values as all uppercase. Again, with all elements of style, make sure that you are doing what the rest of your project is or that you're being self-consistent within your project. We'll run that test again, and sure enough, I got the same input, but let's say that I wanted to support 10,000. Well, I can do that. Now, we didn't get that error. That's why it's a good idea to centralize your constants. But let's continue. Now that we've caught and reported an error, now let's make sure that it actually reports an error. Yes, a runtime error. So now we have truly caught this case correctly. Well, now that we have that, we have to read an array. And I'm going to give it the count and the array I want to read into. You pass an array by just giving the name of the array, and it really just passes a pointer to the first element of the array. And then I'm going to tell it to reverse the array, again with count and the array. And then I'm going to tell it to print the array. Notice that I haven't actually defined any of these, but what I've just done is just by saying, hey, I'm going to define some functions that will do this for me, I've structured my solution in a way that each piece is well contained. The count is an int, so we'll pass it as an int. And the array is an array, so we'll pass it as an array, though we could pass it simply as int star. We'll use a for loop. I, j, and k are common indices. That kind of comes from mathematics. If you've got lots of indices you're using to reference lots of arrays, you might want to give them good names other than I, j, and k. But in this case, we'll just go from 0 to I less than count. Remember, we are 0 indexed. That means that if I have n elements in the array, element 0 is valid, but element n is not. The last valid element is n minus 1. And then we'll just simply read into the ith, that's how one pronounces that, element I in the array for all of count. Well, what do I need to do next? I need to reverse the array. Again, we need to tell it the size of the array that we're handing to it. And I have said I can simply pass it as a pointer, which I will here. And we need to reverse it. Well, what's a good way to reverse? I'm going to do it kind of in pairs. I'm going to say, given the beginning equal to 0, and the end equal to count minus 1, that is the last one, or I can say, let's call this the left end, left and right, and going until, as long as left is less than right, we'll increment left, and we'll decrement right. We're going from both sides to the center. Well, what I need to do is swap the entries of array left and right. Let's go ahead and say that we'll do that with a function as well. We want to do that by saying I'm going to swap the address of array of left and the address of array of right. Why did I give it the address? I gave it the address because I want both these values to be changed, and if I want swap value to change them, I need to send them by reference, and in this case, using pointers. Void swap val takes an int a, an int star a, and an int star b, so I have pointers to two variables. And since I'm going to swap the values, I need to save off one of them because I'm about to overwrite it. If I hadn't saved A at the end of this line, I wouldn't have any A anymore. There is a trick to do this using bitwise XOR operators, but that's a bit of a parlor trick that I will leave for another time, another person to show you. This is the classic swap algorithm. You put the one value into a temporary value, you assign it, and then you assign the temporary to the other value. So all that's left to us now is to write our print array. Again, it will take the count, it'll take the array, and just like in the read, we'll just say for I equals 0 and I less than count. Remember, it is the 1 minus count entry that is the last valid one. And we'll just go to cout with it. I'm also outputting a space so that the numbers aren't just run together, because that's in the output format. So I've written my read array, I've written my reverse array, I've written my print array. Let's see how this goes. Well, we passed the simple case. And we passed all of the other cases. Well, that's good. And what we did is we took a very straightforward approach to this problem. We defined a series of functions that would cover the needed capability, and then we wrote those functions. This is how you successfully break down a problem. We additionally checked for the validity of the input to make sure we weren't going to cause our program to break. And finally, we used a constant such that I didn't have to type in a magic value multiple places. All right, how could we make this better, or what else could we learn from it? Well, for one thing, if we always know that we want to simply print an array in reverse, why don't we write a function that prints the array in reverse? It would take the same arguments but instead it would print them from last to first. Going from last to first would look like I equals count minus 1 and I greater than 0. Greater than or equal to 0. So as long as we have I starting with the last element, which is count minus 1, and we're going to and including the first element 0, then we're printing the array in reverse. Let's try that. This saves us from having to copy the elements. Oh dear. What did I do wrong? I know what I did wrong. Notice I started at a big number and I tried to go to a small number, and then I incremented my index. Cut and paste is evil, and I made one fewer than the needed changes to make the cut and paste work. Notice it compiled correctly, it just came out with gobbledygook. In fact, let's see what it actually did in that failure to see if there's anything else to learn from it. Notice we get a whole lot of gobbledygook out there. We get the last element correctly, and then we get some zeros, which is the compiler being nice and initializing pieces of my stack to 0. And then we get real gobbledygook And then we get a segmentation fault because I kept going and going and going and going until I finally tried to read an array entry that was so far away from a page I'd been given to write on that the operating system said, no, 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 you can't do that. So that is a great example of an array out of bounds where the index is going crazy. I'm starting at the last element and then I'm going forever. I'm never going to stop because if I keeps increasing, then I is never going to be less than 0. That's a pretty classic error. I'm glad I did that. Fixing the index, we have it. Well, what's another way we could do this? Well, remember I said that arrays are like pointers. So what if I simply wanted a for loop that said, starting with an int pointer, which is, and I'll just call it element, and it is the array, the address of the last valid element. And while the element is greater than or equal to the array, I'm now comparing addresses. I'm pointing to the last element in the array, and I'm saying as long as I haven't gone back and passed the first element of the array, then I can take a step backwards this way. And now, to print this, I print the value of the element. Let's see what this looks like. We passed. Do you see why we passed? We were able to go through a for loop, not just with the index, but with the pointer itself. So each time I went through the loop, I pointed to the element ahead. When I add or subtract to a pointer, that moves it to the next valid object of that type. So it moved it 4 bytes. If we were to dump to CR what we're doing here, you would see, and let's do that. End line, remember, is a way to get it both to write a new line and to flush output. And let's look what we got. We started at 0 Charlie, and then we came back to 08, 04, and 00. We changed by 4 each time, I believe. Charlie minus 8 is 4, 8 minus 4 is 4, 4 minus 0 is 4. And there we have it. The pointer was moving backwards through memory, pointing at different elements of the array. Remember that the array itself is simply pointing to the first one. If I were to, and let's go ahead and do that, to print out the array value, you would see that the array is at 20. And the last element I printed is here at 20. So this is the 0th entry plus 1, meaning 4 bytes, meaning 1 integer. That's the first entry. That's the 1th entry, the 2th, and the 3rd. 1, 2, 3, count was 4. So 0, 1, 2, 3 are all valid. We went in reverse order, and we went from 2 Charlie down to 2, 0, and we're done. I left in a bunch of prints. Sometimes it can tell you, oh, you took too much time. So if it does that, go check to make sure that you didn't leave a bunch of print in the way I did. Okay, so that got rid of our need to reverse the array. Well, let's go back and let's say we needed the array in reverse order, so that makes this less of a trivial problem. Can I use pointer logic to rewrite reverse array? I sure can, because if I say star left equals array, that's the first element, and star right is the last element, which is the same as array plus count minus 1, meaning we want the address of an integer that is count minus 1 away from array. It's exactly the same as the address of the last entry in the array. Notice that the increments are exactly the same, but now all I have to do, since these are already pointers, is pass left and pass right directly to swap. We'll give it a different name, and we'll try it. Let's get rid of this so I don't double print. And again, we pass. We should pass all cases again. I'll point out a couple of things about this reverse. Notice that I don't care about the case where left equals right, because if left equals right, that means that I've got an odd number of entries, and left and right are pointing at the same entry, and if you swapped it with itself, it would just be the same. Let's try breaking this. Let's imagine that in this case, I change the pointer so it doesn't decrement, that it goes the wrong direction, it increments. Anybody imagine what we're going to see? We're going to see another segmentation fault, and you're going to see it inside swap val. And we see it inside swap val because eventually one of these addresses got outside of the bounds that we were able to do it. And again, looking at what array is, were we to print what array was here, we would say, hey, right has gone very, very far away from array. Does it matter what order the swap happens in? No, it does not. What if I had tried the naive swap that I said wouldn't work? What would that look like? It's nice and symmetric. The two endpoints are the same, the two metals are the same, because what I'm doing is I'm setting, in the way that I'm using it, that A and B are both getting the value of B. And you can see that this expected to see these B values here, and I just mirrored them. So instead of swapping, I mirrored. So that doesn't work, but that's what that would look like. And this has been a long episode. It's a challenging subject. I hope you will find a lot of useful information in that arrays and pointers are kind of kissing cousins to each other, that an array points to the first element of an array. It is the address of the first element of the array, and that when you do pointer math, when you add or subtract 1 to a pointer, you're going to the next object of that type. If it's an int pointer, you're going to the next int. And thus, you can use pointer math and index math interchangeably. Well, I'll see you next time when we'll go even deeper into arrays in the variable array challenge. That's going to be exciting too, and I'll see you then.